This lecture series is getting a little bit long, so I'll go ahead and skip the proof of the power rule for integer values. But basically, if you look at all the algebra of how this works and you try working on the difference quotient, say for x to the fourth and x to the fifth, you'll see that there's a very common pattern, and that pattern always holds for x to the k power. But let's go ahead and practice using the power rule and applying it. And just to sort of recap the last video, the power rule always states that if I have x to the n power, the derivative is always equal to you drop the power and subtract 1. So, if I drop that 3 out front and then take away 1, I'll always get the respective derivative, and that pattern holds. And using Leibniz notation, we often would write it like this: d dx of x to the k, which means the derivative of a power function such as this, will be equal to k times x to the k minus 1, aka drop the power, subtract 1. Let's do some examples. So what is the derivative of x to the 7th? Well, we can always start by dropping the power and subtracting 1. That's it. Easy game, derivatives, done. And this same idea will hold for anything. So what about x to the 42? Drop the power, subtract 1, 42x to the 41. And again, you can always confirm these by doing it using the definition of the derivative, the limit of the difference quotient. But for this one, it'll take forever, it'll be really, really boring, and you're gonna get this answer anyways. The power rule works no matter what, assuming it's a power function. And again, assuming k is not 0. That is something. Actually, no, it does work for k is equal to 0. I lied. So never mind. I'm thinking of a different rule for integrals, which comes later. So actually, let me go ahead and amend this note, which I said in the last video. Actually, it does work for k is equal to 0. That's a silly case anyways. It would just be the derivative of a constant, which is always 0. Anyways, what about the derivative of just x? So technically x, you might say, well, this doesn't look like x to the k, but remember, if x is just by itself, you could always pretend, or not pretend, but there is technically, it just means there's a lone singular x, which is equivalent to x to the first power. Now, if I apply the power rule here, I would drop the power out front and subtract 1. Well, 1 minus 1 would leave me with 0. And if you remember the rule of x to the 0 power, anything to the 0 power is always 1. So what this would leave me with is 1 times 1, or 1. And this would give me the same derivative. Basically, this is a very important derivative to remember. Derivative of x by itself is always 1, because this is linear and this is the slope. This also makes sense. And remember that when you're doing d dx of something, this will give you the slope of the respective value. And these are all slopes of the original algebraic expression. Well, what about negative powers? This works for negative powers, it works for fractional powers, but basically, if I have x to the negative 7th, I drop the power. That includes the negative, because that is part of the exponent. And then I would subtract 1 from the negative 7. Remember, since it's a negative, if I take away 1, that should become negative 8. So what that would leave me with is negative 7 times x to the minus 8th. Or a more proper way of writing it, usually it might ask you to write it with positive exponents only, but basically, this would be, remember that a negative exponent is the same as a reciprocal or dividing by. You can always flip it and make it positive. And remember that negative 7 will stay on top. But basically, what this would give me is, again, I would lose 1 power. Notice it actually looks like it's gaining a power, but that's only because it was a negative to begin with. And when you take away from a negative, it gets, well, technically smaller, but the absolute value gets larger. And the reason I bring this example is, let's say I wanted to figure out what's the derivative of 1 over x squared. Well, remember that a reciprocal such as this, you can always rewrite using a, whoops, I'm in the wrong spot, using an exponent. So this is equal to d dx of x to the negative 2 power, because 1 divided by x squared is just equal to x to the minus 2. And now that I've switched it to a negative, it's easier to use the power rule. So first of all, you cannot use the power rule directly on this, because power rule only works on x to the n. It does not work for 1 over x to the n. So this is not 1 over 2x. That's not going to work. So I have to rewrite it using exactly the form x to the k. Now it will work. So again, to take the derivative, I drop the power out front and subtract 1, which would give me negative 2x to the minus 3. And again, a more common way of writing that would be negative 2 divided by x cubed. That would be my derivative in this particular case. In the next video, because this one's getting a little bit long, let's look at what happens when we have fractions or decimals in our power functions.